That's right, we're doing it. But before we get started, let's get some basic things out of the way first. I'm using a tank hull, but you can use any vehicle you like. I suspect most of you are using a car, truck, or wheeled vehicle of some type. We're only going to be dealing with the gearbox today, so make sure you already have chips that control throttle and steering. I'm using CTMC, but only for the throttle and steering. Make sure you have a speedometer with split outputs to XYZ ticked, and that it is welded or well parented to your base. Finally, we'll need a power controller to actually drive our contraptions. Before we get started in the E2 editor, I want to talk a bit about how the transmission should work. It's an automatic transmission, alright. It should automatically shift gears as I drive around, but in what manner specifically? I'm gonna cheat a little for you. One way it could work is via the RPM of the engine. If the RPM goes below the bottom of the power band, the gearbox downshifts. If the RPM goes above the top of the power band, the gearbox upshifts. This is not the automatic gearbox we'll be making today. Instead, this automatic transmission will shift on speed. For example, Gear 1 is good for 0 to 10 miles per hour, I'm American by the way. Gear 2 is good for 10 to 20 miles per hour, and Gear 3 is good for 20 to 30 miles per hour. All the E2 would have to do is look at the speed of the tank and shift to the corresponding gear. Another thing to consider is that I want the automatic transmission to work when driving forwards and in reverse. If you've ever ridden a car with an automatic transmission, you know what a Prindle switch is: park, reverse, neutral, drive, and low. Depending on where the lever is, the transmission will be in a certain mode. I want this transmission to have two modes: drive, or just forwards, and reverse. As far as how the Prindle switch should work in terms of the E2, when I press W, I want the transmission to be in drive, and when I press S, I want it to be in reverse. For inputs, we'll have W, S, and speed. For outputs, all we'll need is gear. I'm also going to add a persist variable, Prindle. The names for all these variables doesn't actually matter, just make sure you know what each of them are for. I'm setting trigger to none so that none of the inputs causes the expression to execute. I'm going to make an if statement with first or do finished for instructions that need to get ran at the start of the expression. Now I'm going to add an interval timer for every 105 milliseconds. Now for the Prindle switch functionality, I'm going to make an if and else if statement so that when I hit W and S, Prindle will be set to 1 and 2 respectively. Now I'm going to make some more if and else if statements using Prindle. This is, again, so I can differentiate between forward and reverse drive modes. Also note that I had to use two equal signs in the parentheses. Now for a more tedious part, I'm going to make a bunch of variables storing the speeds at which the transmission needs to shift. Something that you might catch is that my reverse speeds are also positive, and that's because I'm going to be taking the absolute value of the speed of the tank. Speaking of speed, I'll make a new variable. This one doesn't have to be a persist, that'll be doing just that, taking the absolute value of the tank's speed and converting it to miles per hour. Now back to the core of the transmission. I'm going to use an if, a bunch of else if, and an else statement. The way this will work is the speed of the tank gets compared to each of the shifting speeds, and if the speed of the tank is lower than that speed, then that gear gets selected. This will work because the conditions of an else if statement are only checked if the conditions of the prior else if or if statement aren't met. The else statement is only used if all the previous conditions failed. If my speed were 15, the first if condition would be checked, but because 15 is greater than 10.8, the E2 goes on to the next else if statement. 15 is less than 21.7, so gear 2 gets selected. And of course, we're going to need to use a similar setup for reverse. And of course, don't forget to wire your inputs and outputs. Speed will just get wired to the Y output on the speedometer. Everything else is self-explanatory. So the automatic transmission works just fine. However, one of the problems that I'm having right now is that when I'm going kind of fast forwards and then suddenly switch into reverse, the transmission picks a bad gear. And the reason this is happening is because I'm only taking the absolute value of the speed of the tank. As a partial solution to this problem, I'll have the E2 use the first gear when going in the wrong direction. I'll use the speed input since it includes direction, forward being positive, reverse being negative. This is why the needle should face backwards on the speedometer. For the forward part of our automatic transmission, I'll add an if statement that sets the gear to 1 when the speed is less than 0. For the reverse section, the gear will be set to 6 when speed is greater than 0. An issue arises with this, and that is that the fix won't take effect because the if statements directly after these will overwrite gear. To fix this issue, I'll put the shifting if, else if, and else statements under a whole nother else statement so that normal shifting can only proceed if the vehicle is moving in the right direction. And here you can see that when I go from forward to reverse, the gear is limited to 6, which is my first reverse gear, and when I go into forwards, the gear is limited to 1, which is just my first forward gear. Using a bunch of variables to store the various shift speeds certainly works, but what if you change the gearbox? You would not only have to add or remove some of the variables at the start of the E2, but change some of the if, else if, and else statements that handle shifting. This is all just a very long-winded way of me trying to tell you that there is a better way of doing this. We'll make a new variable, shift speeds, and this variable's type will be an array. Arrays are nice because they have multiple slots, and I'm going to be storing the shift speeds in these slots. I'll make 2 more variables, top gear and gear count, and what these will do is set boundaries for what are forward and reverse gears. For me, these are gears 5 and 8 respectively. Now we need to rework the way shifting is handled so that it functions off the array's indexes and takes into account the forward and reverse gear restrictions. To figure out if the transmission should upshift, we'll index using gear and check if the speed is greater than that particular entry. To figure out if the vehicle should downshift, we'll just use the previous entry, gear -1, and check if the speed falls below that entry. We're using the gear variable to index because at any given point that is what gear the transmission is in. Now for the restrictions. In our upshifting if statement, we'll add an AND check to make sure the gear is less than the maximum forward gear. In the downshifting else if statement, we'll also add an AND check, but this one will check if the gear is greater than 1. Both of these are in place to make sure there are more gears to shift to. Now to actually set the gear when upshifting, I'm going to write gear, then ++ immediately afterwards. This will increment the gear variable by 1. It's the same thing as writing gear equals gear +1. For downshifting, we'll write gear -. The reverse part of the shifting algorithm should look very similar to the forward part, the only difference being our gear constraints. I'm also going to replace gear 6, which is my first reverse gear, with top gear +1 for the gear limiter when going the wrong way, and also for my downshift constraint. And to prove to you that this does still work, I'm going to take this vehicle for a test drive. This all might not make very much sense to you, so it's nice to imagine what happens when the vehicle is driving forwards with a speed of 30 miles per hour and a current gear of 2. The E2 is comparing the current speed, which in this case is 30, to shift speed's gearth entry, which in this case is entry 2, or 21.7. There's an upshift, because 30 is greater than 21.7. What if the speed of the vehicle was 8 miles per hour and the current gear was still 2? The conditions of the first if statement would not be met. 8 is not greater than 21.7, so the else if statement is checked. The E2 then compares the current speed, which in this case is 8, to shift speed's gear -1th entry, or 10.8. 8 is less than 10.8, so there's a downshift. Now if the speed was between 10.8 and 21.7, both statements would fail and the vehicle won't shift. The E2 will maintain the current gear. The nice thing about using an array to store the shift speeds is that if you do need to change the gearboxes for any reason, all you need to do to get the E2 running again is change the settings under the if first or do finish statement. You don't have to keep changing the core code. And now for a bit of a bonus. I'm lazy and don't like having to find out the new shift speeds every time I change gear ratios, or gearboxes. I'm going to make the E2 do that for me. The specific magic we'll be doing involves the measurement of a circle and the rotation rate of said circle. If you were to take the diameter, which is the length from one side of a circle to the opposite end, or twice the radius, if you took this length from one of my road wheels and multiplied it by 3.14, which is an approximation of the number pi, you would get the perimeter of the wheel, or more appropriately, the circumference. You can imagine this would be the length of the line you'd get if you unraveled the wheel. This length is kind of significant because it is the linear distance, in inches in my case, the wheel moves after a full 360-degree rotation. If you knew the revolutions per second of the wheel, yes, I said revolutions per second, not revolutions per minute, you could very precisely calculate the linear speed of the wheel, again, in inches per second. So now we need to figure out the rotation rates of the wheel at which the transmission needs to shift. This might sound a little confusing, but we'll start at the engine. The top of the power band of this multi-fuel V10 is 1,900 revolutions per minute. The top of the power band is generally where you want to shift. Because we want revolutions per second, we'll divide this by 60 to get 31 2/3 revolutions per second. The reality is, however, the wheels won't even be rotating that fast because this number assumes a total gear ratio of 1. Let's go through a mock calculation of the wheel speed in first gear. We already know the unreduced speed. Now we need to multiply this by the total gear ratio, and this total gear ratio is the product of gear 1 and the final drive, 0.1 and 0.6 respectively. The total gear ratio for gear 1 is 0.06, which if we multiply by the unreduced rotation rate, yields 1.9 revolutions per second. Now to multiply this rotation rate by the circumference of my wheel, the circumference being 100.719 or 32.06, my wheel's diameter, times pi. I end up with 191.367 inches per second. Dividing by 17.6 to get miles per hour, that number becomes 10.87. This, as I'm sure you're aware, looks awful familiar. That might have been painful to listen to, but now that I've explained how this works, let's have the E2 do this for us. We'll make two entity inputs, engine and gearbox. I'm gonna go down and make a few temporary variables, one of which being wheel size, which will be equal to my road wheel's diameter. I'm gonna make another variable called final drive, and this will be equal to my gearbox's final drive, or 0.6. Now I'll make another variable called engine RPS, and set it equal to the top of the engine's power band divided by 60. Again, I'm going to make another variable called wheel circ, and this will be the wheel's circumference. Now I'm going to set up a for loop. The first part, I equals 1, is there to initialize a key. I think it's called a key anyway. And I'm going to use that I variable as an index for a few things. The second part, which I set to gear count, is how many times the for loop should loop, which is 8 for me. The last part is the step, or how much is added to our key, I, after each cycle. We'll just leave that to 1. The first variable inside the for loop will be total ratio, and this will be equal to the absolute value of the ith gear ratio times the final drive. Make sure both the gear ratio and the final drive are in the parentheses of the ABS function or you'll get an error. Our next variable will be wheel speed, and this will be the product of the engine speed in revolutions per second, the total gear ratio, and the wheel's circumference. Now we'll get the shift speeds array down here, and set its ith number equal to the wheel speed divided by 17.6 because the wheel speed is still in inches per second. Now to see what the chip comes up with, I'll have the E2 print the shift speeds array. Alright, time to update the E2. So when I update this, you can actually see that it did print an array to me, but the array's full of all zeros, and the gear count is still 8, the number of gears in my manual transmission. So you can see 1, 2, 3, 4, 5, 6, 7, 8. But the reason the chip is printing all zeros is because the engine and gearbox haven't been wired yet, so make sure you wire those two. And now when I update the chip, now it has basically all the same shifting speeds I was using before, and you can see they're all positive. And I'm not going to take this vehicle for a test drive because the shifting part of the Aw-Toe-Magik transmission is still the same. The E2 is basically coming up with the shifting speeds without me having to enter them, which is nice. Well, that's all I have to show you right now. In closing, I do want to say that there are many ways to accomplish the same basic thing in E2. There are certainly better, and worse, ways of doing this. There's also nothing stopping you from adding more features to your own code. It's also kinda neat how you can get an E2 to come up with the shift speeds automatically, granted with some basic information, and handle the actual shifting of the gears, all while being well under 100 lines. A few of you might recognize this code as well, and that's because CTMC uses basically the same system for finding shift speeds and shifting. Maybe the variables have different names and everything isn't quite as organized, though. Late in the process of making this video, I've also noticed that the gear selector part of the code looks suspiciously similar to ACF's own automatic transmission code, which looks like I stole it. Whoops.